Hello there. I'm just going to do a brief tutorial to answer a question that was mailed in about writing a Python function to calculate binomial coefficients. So I'm going to start off here in a Python file with some triple quotes there, which lets me write whole paragraphs of text. And let's just make a brief note of what it is we're trying to do. So the binomial coefficients are expressions of the form, well, we say n choose k, and the value of n choose k is n factorial divided by k factorial times n minus k factorial. So that's one way to write them. And if we'd already written a factorial function, then we could write them directly like that. So I'm just going to start off by showing you that way of calculating binomial coefficients. So the first thing we'll do here is write down a factorial function. So the factorial of x, there are many different ways to do this, but I'm going to do it recursively, which means I'm going to write a function which uses itself. So the factorial function can be defined this way. If x is 0, then we give the answer 1. Now if x isn't 0, then we'll reach the next line below. If x was 0, then return will have had the effect of quitting the function and returning with the value 1. So we know that if we ever reach this line underneath, this line here, that x wasn't 0. So in the case where x isn't 0, the factorial can be given by x times the factorial of x minus 1. So that's the usual way of writing the factorial function recursively. Now, as usual, when we've written a function, it's a good idea to test it out a little bit. So what I'm going to do here in the main program is just to test it a little bit. So let's see if our program can calculate the factorial of 0 correctly. And let's also get it to calculate factorial of 1 and factorial of 2, just for now, just to see if things appear to be working right. So let's run this program, and we see 1, 1 and 2, which are the answers that we expect. Okay, that's not a very thorough test. What I could in fact do is put a loop in there and print the first few factorials. So here I'm going to let k go from 0 to 9, which is the range 10, and print the factorial of k each time. And it'd be helpful for us to print k as well, so that we can compare. So let's run this code. And if I scroll up, so 0 factorial gives 1, 1 factorial gives 1, 2 factorial gives 2, and so on. So if you check these, you'll see that they're correct. If you check them with the definition of factorial. So armed with a factorial function, we could write a binomial coefficient function straight away. So binomial needs two inputs, n and k, to calculate it, and its value is given by the expression up there, which is factorial of n divided by, and now we've got to be careful here, we need some brackets, factorial of k times factorial of n minus k. So that's one way to do binomial using our existing factorial function. Now there's one thing to be wary of here. We're doing a division in the middle of this expression, and usually division involving integers is a dangerous thing to do, because unless the answer is itself an integer, you don't necessarily get the correct answer. Python and many other programming languages will give you just the integer part of the answer, not the full answer itself. However, we don't really care about this here because we know that binomial coefficients are whole numbers. So the answer to this division must be a whole number. So in this case, it's actually safe to do this division with an integer on the top and the bottom. Okay, now we should really test this out. And so let's test this piece of code. Now we have both n and k to play with here. So let's perhaps have a loop where n goes through some range, and for each value of n, k goes through some range. Now we've got to be a bit careful here. The binomial coefficients only make sense if k is between 0 and n. So what we need to put in here is, to get k to go from 0 to n, we need range n plus 1 there. So that will go all the way from 0 up to n. Now in here, indented, now we could print the value of n and k and the binomial coefficient n choose k. That was a quick way of testing this. Now of course quite a few numbers are going to be printed here, so perhaps for now I'll reduce this number 10 down to say just 3, just to check what's happening. Let's give it a go. Okay, so we get 0 choose 0 is 1, 1 choose 0 is 1, 1 choose 1 is 1, and so on. So you could test this with the definition of binomial, but that looks okay to me. Now there's something we ought to be a bit wary of here. In our factorial function, the factorial function uses itself, calls itself with the value x minus 1. And the idea is that if you put a positive integer in for x, that this function will keep on calling itself with smaller and smaller values until it hits 0, and then this piece of code will be run, which is the base case for the recursion. Now, what if we put a negative number in for x? Then we're in real trouble here, because instead the function will simply keep on calling itself forever. So what we should really do is an error check here at the very beginning. We should assert, so we should state that x should not be 0. So we assert that x is not 0, and we can put a piece of text here to come up on the screen in the case where someone puts in a bad input. So we could put something like factorial not defined for negative x, and that would help us a lot there. Okay, so let's just check this still runs. Oh, interestingly, I'm seeing this error. I put x non-zero. Of course what I meant to say was x greater than equal to 0. So we need x to be greater than equal to 0, otherwise factorial is not defined. And there we go, the code runs as normal. Let's just check that it can fail. If I were to put in here factorial of minus 3, something like that, then we get that error, factorial not defined for negative x. So now we've got a bit of error checking there. Now the other thing that we could do to calculate binomial coefficients is to use the recursion relation for binomial coefficients. So the binomial coefficients form what's called Pascal's triangle. And that's the triangle in which every entry is the sum of the two entries above it. So there is Pascal's triangle. I've not drawn it out in a particularly good way. Let me respace it a little so it looks more like the conventional form. So notice in this triangle, each value here, for example the 3, is the sum of the two values directly above. So how can this help us? Well, each row in the triangle corresponds to a value of n. So if I just label these rows here, the top row is when n is 0, the next row down is when n is 1, and we have n being 2, n being 3, and n being 4. Now the position of the number in each row is given by k, and k goes from 0 up to n. So this whole left hand side here of 1s corresponds to k equals 0 each time, and the ones on the other side correspond to the case where k equals n each time. So the edges of this tree give us edges of this triangle give us base cases, boundary conditions, in the same way that x equals 0 does here for the factorial function. So we could detect if we're at the edges of this triangle and give the value 1, and if we're not and we're inside the triangle, then the value we want is given by adding up the previous two values on the row above. Well, the row above must be row n minus 1, and the positions here must be k minus 1 and k. So I'll just write myself a note here. So this suggests a recursion relation, and that is that the binomial value for n and k can be the binomial value for n minus 1, k minus 1, plus the binomial value for n minus 1, k. Okay, now we can't always use that. We can't use that if we're at the edges of the triangle, so we've got to be a bit careful with this. We can use this relation if we're inside the triangle, but at the edges of the triangle we've got to do something else. Okay, let's see if we can figure out how to write the boundary conditions for this. So the first case I'm going to look at is to see what would happen if we had k equals 0 here. So if k is 0 for any given value of n, then that means we're on the left hand side of the triangle, and the answer we get is always 1. So binomial n0 is always 1. If we're on the right hand side of the triangle, which corresponds to k equal n, so binomial nn, then we also get a 1. So that's another way that we could write this down. So let's just recap. So we want the binomial to give us the answer 1 in the case where k equals 0 or k equals n. If neither of those are true, then we want to use this recursion relationship down here. So let's try writing it this way. So I'm going to define another function. I'm going to call it binomial 2 because I've already used the name binomial. It needs two inputs n and k, and now our special cases, our special conditions, are if k happens to be 0, then we would like to give the answer 1. Now, since return quits the function, then if we ever get to the next line, we know that k wasn't 0. So what we could do is the following. So we could have another if statement. If k is n, then we also want the answer 1. And once again, if we ever reach this next line here, then we know that we didn't have the case k equals 0 or k is n. So in that case, we want to return the answer of the recursion relation, which is binomial n minus 1, k minus 1, plus binomial n minus 1 and k. So that's one way to write this. Now again, we should really be a bit careful. If someone puts in a negative value for k or n, then we could have some problems here. So we want to put some tests at the top, really. So we really want to assert that n is greater than or equal to 0. Otherwise we should perhaps give some text, binomial not defined for negative n. That's one thing we could do. Also, for any given value of n, we do need that k lies between 0 and n. So we need k greater than or equal to 0 and k less than or equal to n. Once again, we could give a message. So there we go. So we've given an error message in each of those cases. So if neither of those nasty cases come up, then we drop through to this next line. We check if k is equal 0, in which case we're on the left hand side of the triangle, and we return the answer 1. We check if k is n, in which case we're on the right hand side of the triangle and the answer is also 1. Otherwise, we know that we're within the interior of the triangle somewhere, and you can get the binomial coefficient by adding up the two previous ones on the row above. Now the row above must be row n minus 1, so we have n minus 1 in both cases, and the two positions above are position k minus 1 and k. So let's try that. Since we already have an existing binomial function here, let's also then write down the result of applying our new one and check that they match. Okay, so let's run this and see what happens. There we go. So the result of our original binomial program is that column there, and the new recursive binomial program is this column here, and you can see that they match for all the values we've tried. Okay, so just a quick recap. We figured out what the binomial coefficients are, and they have this definition usually in terms of factorial function. So we started off implementing a factorial function and wrote a binomial function using it. So that's the first thing that we tried to do. The next thing we did was to notice that the binomial coefficients form this nice triangular pattern, in which in the interior of the triangle each binomial coefficient is the sum of the two directly above. We also, so that defined this recursion relation here, but we also noticed that there are boundary conditions or base cases for this, which are the left and right hand sides of the triangle. In each case we have the answer 1. So when we came to write this, we wrote a new binomial coefficient function which takes two inputs n and k. First, it checks that these inputs make sense, that they are in a valid position in the triangle. Secondly, we test if we're at the edges of the triangle and return the answer 1 in both cases. Otherwise, if we haven't returned by then, we drop through to the bottom line here where we use the recursion relation. Now notice here, actually, in the case where k equals 0 and in the case where k equals n, in both cases we return 1. So we could actually change this code around a little bit to make it look a bit more readable, and we could say that if k is 0 or k is n, then return 1. And we could do away with one of these if tests. So that makes everything a bit more readable. So if k happens to be 0 or k is n, the answer is 1. If we haven't returned by then we drop through to the next line and we use the recursion relation. Let's just run that and check it still works. Okay, thanks for listening.